The interstellar object 3I/Atlas, which entered our solar system after traveling through interstellar space, has been a fascinating object of study ever since its discovery. One of the most intriguing aspects of this object is its rotational dynamics and how it behaves as it passes close to the Sun. The rotation period of 3I/Atlas has been measured using two methods: tracking the orientation of the jet structure launched by the object as it rotates, and observing periodic changes in the object's brightness, including the halo of the coma and the jets. These periodic modulations provide a window into understanding the object's physical properties and the forces at work on it, especially as it approaches and passes through perihelion, the point in its orbit closest to the Sun. Recent studies, including one co-authored by Tony Scarmato and myself, have measured the rotation period of 3I/Atlas after it passed through perihelion on October 29, 2025. Our observations were based on two different methods that yield slightly different but complementary results. The first method involved the detailed analysis of images from the Hubble Space Telescope, HST, taken between November 20, 2025 and December 27, 2025. We applied the Larsen-Cecchinina rotational gradient filter to the HST images, which allowed us to measure the position angle of the anti-sunward jet at multiple points in time. The second method involved observing the brightness variations of 3I/Atlas between December 9 and 22, 2025, using data from the 0.25-meter telescope MPC L92 located in Calabria, Italy. The results from both methods revealed that the rotation period of 3I/Atlas is approximately 7.1 hours. More specifically, the position angle of the jet structure on the sky showed periodic shifts of approximately plus or minus 20 degrees, with a period of 7.20 plus or minus 0.05 hours. Meanwhile, the brightness variations, a result of the dust and gas emitted by the object, showed periodic changes of about plus or minus 30%, yielding a slightly different period of 7.136 plus or minus 0.001 hours. The slight difference between the two values is likely due to systematics and aliasing, but the combined data suggests that the post-perihelion rotation period is approximately 7.1 hours. This rotation period, which governs the periodic precession of the jet structure around the rotation axis of 3I/Atlas, represents a significant shift compared to pre-perihelion measurements. Prior to perihelion, the object exhibited a rotation period of around 16 to 17 hours, which was inferred from the observed brightness modulation of the object. However, after perihelion, the rotation period was found to be about half that duration, at approximately 7.1 hours. The change in rotation period after perihelion raises several important questions, particularly about the causes behind such a drastic shift. The alignment of the rotation axis of 3I/Atlas with the Sun 3I/Atlas axis is another intriguing finding from our study. By associating the average position angle of the jet with the rotation axis, we inferred that the rotation axis of 3I/Atlas is aligned with the Sun 3I/Atlas axis to within 20 degrees. This alignment is surprising because the object was set in interstellar space, far from the gravitational influence of the Sun, and it is unlikely that such a precise alignment would occur randomly. In fact, the probability of this alignment happening by chance in interstellar space is very low, around 1.5 to 6%. This rare alignment could have important implications for our understanding of the forces acting on 3I/Atlas as it travels through the solar system. It is essential to understand how the perihelion passage may have triggered this change in the object's rotation period and the alignment of its rotation axis. The perihelion passage of 3I/Atlas involved a dramatic increase in mass loss from the object, as evidenced by the images taken by the Hubble Space Telescope. Less than 1% of the scattered sunlight observed in these images originated from the surface of a nucleus of 3I/Atlas, with a majority of the light coming from the glowing coma and jets surrounding the nucleus. The mass loss rate increased significantly as the object neared the Sun, and this increase in activity could have had profound effects on the rotational dynamics of the object. One possible explanation for the shift in rotation period is the increased activity in the coma and jets of 3I/Atlas. As the nucleus rotated, the dominant outflow direction of dust and gas would have swept around the rotation axis, producing periodic variations in the observed flux of scattered sunlight. This phenomenon, referred to as heartbeat variability, occurs as the jets release dust and gas into the coma in a manner akin to a heart pumping blood through veins. The periodicity of the brightness variation seen after perihelion is likely tied to the precession of the jet structure, which modulates the column density of dust along the line of sight and changes the scattering properties of the dust particles in the coma. This precession around the rotation axis produces periodic shifts in the jet orientation, which in turn modulates the observed brightness of the object. It was initially thought that the brightness variations observed in 3I/Atlas were due to changes in the reflected sunlight from the rotating surface of the nucleus. However, our study and previous work have shown that this assumption was incorrect. Instead, the brightness variability is a result of the jet-driven modulation that tracks the rotational state of the object through the shifting orientation of the jets, rather than direct measurement of sunlight reflected from the surface of the nucleus itself. This means that the observed periodicity in the brightness variations corresponds more to the jet orientation and its periodic precession, rather than the rotation of the nucleus. Another important consideration is the change in the number of active jets on 3I/Atlas. Before perihelion, only one rotation pole of the object was illuminated by the sun, which likely resulted in a single active jet being visible from Earth. However, after perihelion, both poles of the object were illuminated by the sun, potentially activating two jets that would have been viewed from a different angle. This change in the number of jets could explain the observed doubling of the frequency of brightness modulations, as the precession of the jets becomes more pronounced with the activation of a second jet. The alignment of the rotation axis with the Sun, 3I/Atlas axis, likely facilitated this change, as the Sun's illumination could have triggered additional active regions on the surface of the object. In conclusion, the post-perihelion rotation period of 3I/Atlas is approximately 7.1 hours, as measured through both jet position angle shifts and brightness variations. The observed periodic wobble of the jet orientation around the rotation axis did not change during perihelion, but the alignment of the rotation axis with the Sun 3I/Atlas axis is anomalous and requires further explanation. The change in rotation period and the increase in jet activity are likely a result of the perihelion passage, which triggered a new phase of behavior for the object. The data suggest that the precession of the jet structure, rather than changes in the nucleus itself, is responsible for the observed brightness variations. The alignment of the rotation axis with the Sun 3I/Atlas axis is a rare occurrence in interstellar space and presents a fascinating puzzle for astronomers to solve as they continue to study this remarkable object.